10. I promised you a word problem where we have to find an absolute max or min in the context of a biological application. And before we go there, though, I want to show you again, there's one very familiar slide by now, that we're finding an absolute max or min for a function of two variables on a closed bounded set. And in math 136, these sets are restricted to rectangles and triangles. All right, and again, I want to emphasize, I cannot emphasize this enough, that these absolute maxes and mins can occur either at the interior at critical points or on the boundary, right? So we need to be careful to check both of those situations. All right, so let's go back to an example that we considered in week number 9 on Thursday, the last time that we saw each other in person. During that lecture, we considered a model for the basic reproduction number for the spread of SARS. And remember actually that the basic reproduction number represents the average number of new infections from one infectious individual. And if R naught is less than 1, the disease will die out. And that is, that's a very good situation, of course. And if R naught is greater than 1, then the disease spreads. And the idea is, of course, to implement measures so that R naught is as small as possible in order to control the spread of a disease. So that's exactly what's happening right now with the coronavirus. We're desperately trying to get the R naught down to a number that's not much larger than 1 and ideally below 1. All right, so we had an expression for the value of R naught as it depends on two really important variables. D, which is the average number of days that an individual remains in the population while infectious, so before they're quarantined or before they realize perhaps that they should self-isolate or quarantine themselves. And V, that's the fraction of the population that is vaccinated. So the question here is that if we restrict our attention to the case where D lies between 0 and 20, you would hope that that nobody walks around while being infectious for 20 days. Then what is the maximum value of R naught? Okay, so mathematically, what we want to do is we want to maximize R naught subject to the explicitly stated constraint that D has to be between 0 and 20, but there is an implicit constraint as well that has to do with V. Because V is a fraction of the population, then of course it has to be true that V is between 0 and 1. You cannot vaccinate more than 100% of the population. And so V cannot be larger than 1. So just to make this clear then, that the first constraint is explicitly stated, and the second constraint is implied, since V is a fraction. Okay, so let's go through the two steps for finding finding the maximum, finding the absolute maximum. So here I've written both constraint out, that D has to be between 0 and 20 and V between 0 and 1. So actually this here is really our set D on which we find the maximum. So this is our set D for this problem. Okay. Okay, and we'll see in a second that this is a rectangle. But let's start with step number 1. So step number 1 is to evaluate R naught at all critical points in the set D. Okay, so to find the critical points, of course, we have to find our partial derivatives. So take the partial derivative with respect to D. So that is 5 times 1 minus v. As far as d is concerned, those are all constants. And then we use the quotient rule to find the derivative of d over 1 plus d. So that's 1 plus d squared. It's 1 plus d times the derivative of the numerator, which is 1, minus the numerator d times the derivative of the denominator, which is 1. And so now our d's cancel out in the numerator, and we are left with 5 times 1 minus v over 1 plus d all squared. And we need to set that equal to 0. Well, there's only one way that this can be equal to 0, namely when v is equal to 0. Okay, let's look at the other partial derivative, partial with respect to v. So that is going to be equal to 5 times minus 1 times d over 1 plus d. So this is minus 5d over 1 plus d. And this is equal to 0 when d is equal to 0. So that means that there's only one critical point. The only critical point is the point dv is equal to 0, 0. And the value of R naught at this critical point is 5 times 1 minus 0 times 0 over 1 plus 0, which is of course 0. Okay, and this makes sense, right? So this makes sense because what does d equal to 0 mean? That means that an individual is quarantined immediately upon becoming infectious. So if d is equal to 0, then an individual is quarantined immediately, the second, basically, that somebody becomes ill. So immediately upon becoming infectious. And that then says, then of course, there can't be any spread of the disease. So there's no spread of the disease. Okay, so that was step number 1. Now what we need to do is take a look at the boundary of the set D. So let's draw that first, actually. So let me write it down first. So step 2 is to analyze R naught on the boundary of D. So let me draw it. So let's put D on the horizontal axis and V on the vertical axis. And D can go all the way up to 20, and V is restricted between 0, V is between 0 and 1. So we basically have this rectangle. And let's label these sides L1, L2, L3, and L4. So L1, on L1, we know for sure that V is equal to 0. And we also have the restriction that D has to be between 0 and 20. And L2, we have D equal to 0, with the restriction that V is between 0 and 1. On L3, we know for sure that V is equal to 1, and we still have that restriction that D has to be between 0 and 20. And then on L4, we have that D is equal to 20, and we have the restriction that V is between 0 and 1. Okay, so actually right away, we can take a look at what R naught is on some of these. So let me use green for that. So on L1, what is R naught? Well, if V is equal to 0, we know that R naught is equal to 5D over 1 plus D. When on L2, we have D equal to 0, so right away that sets R naught equal to 0. So we're kind of done with that one. We know that R naught is going to be bigger than 1. And on L3, when V is equal to 1, we also have R naught is equal to 0. So we don't really have to do any more work on L2 and L3. And on L4, we have R naught is equal to 5 times 1 minus V times 20 over 21, which is equal to 100 over 21 times 1 minus V. So that's what R naught is on L4. And it's really these last two, or well, I should say the first one, I suppose, and the last one. So it's only these ones that require more work. And that's what I'll do on the next page. So these require more work. Okay. So I'm just going to write down again what we had on L1. So on L1, we have that R naught is equal to 5D over 1 plus D, subject to D being between 0 and 20. Okay, and just a reminder that on L1, we have V equal to 0. Okay, so we need to maximize R naught. Well, we know that R naught is equal to 0 when D is equal to 0. But then the question is, what does R naught do when D increases? Well, I can calculate the derivative. So I can take the derivative of 5D over 1 plus D with respect to D. It's a bit confusing with all those D's, but we're taking the derivative with respect to D, and really we've already done this before. It's just going to be 5 over 1 plus D squared. And that is a positive function. Therefore, R naught increases with D. Okay, and that says that R naught attains its max at D equals 20 on L1. Okay, so what then is R naught at when D is equal to 20 and V is equal to 0, because that's what happens on L1, V is equal to 0. Well, this is equal to 5 times 20 over 21, which is 100 over 21, and that's approximately equal to 4.76. That's certainly larger than 0, so at the moment this is the largest value of R naught that we've found. And then we'll take a look at L4. On L4, D is equal to 20, and R naught then is equal to 100 over 21 times 1 minus V. That's what we found on the previous page. And this we recognize as a linear function of V, and it's decreasing with V. So that means that R naught has a max at V equal to 0 on the line segment L4. Okay, and now if you put this together, it's actually the same point. So it's the same point as found above. Okay, so I don't have to do any more work. I don't have to calculate. I've already calculated it above. And so the grand conclusion then is that the maximum value of R naught, subject to the constraint that D is between 0 and 20, that's the one that we were given, is at the point dv is equal to 20, 0. And what is the maximum value? It's R naught evaluated at 20, 0, which was 100 over 21, which is approximately equal to 4.76. Okay, so that's it. That's our maximum value. That's exactly what the answer was. And of course, I have to show you the visualization of this particular problem. So here's the surface for R naught on our rectangle where D goes between 0 and 20 and V goes between 0 and 1. And you can see very clearly that the maximum is obtained right here. So there's the maximum at the point D is 20, V is equal to 0, and R naught is approximately 4.76. So this is the coordinates are D, V, R naught. Okay, and on the contour plot on the right, the lightest colors are associated with bigger values of R naught, and you can see that the maximum is going to be sitting right at the corner at the point dv is equal to 20, 0. All right, that's it. That ends week number 10 material. So thank you for sticking with me as I figured out how to make these videos, and I'll see you again in week 11. Bye.